Okay, someone help me out here. What's the picture you have in your head? Warm up question number 2. Yeah. Okay. So we're just going to look at the area under this curve to the right of 9. So maybe something like this. Okay. So if we're using CDFs, the cumulative density function, how would we find this? Remember, last time we plugged in 5 into the CDF to find the area to the left of the value. How would we do it here?
You plug in 9, but subtract that from 1 because you're given the area to the left of the value.
Okay, very nice. So what Luke is saying is, if we plug in 9 into the CDF, so I have the CDF of 9, this thing is giving me the area that's not, it's like everything except the value we're looking for. So because probabilities have to add up to 1, the whole area of the curve must equal 1. We take 1 minus the CDF, which gives us the area to the right. How many of you were able to get this? So if these things are a little bit unfamiliar, maybe take a look back at some of your statistics concepts, or come to me and ask me for extra practice. But I expect basically everyone in this room to have seen at least some of these things before. We're not going to spend a ton of time on this, but this is some of the foundation of what we're doing with variables. So maybe take a stab at this and try to do it in code. The picture you have in your head should look like this. So we want sleep to be greater than 9 hours. So it's this area. And then we can just do this in Python code. You can copy and paste from the slides if you like, but I recommend you use the code that I've given you already and try to construct this for yourself. You have all the pieces. So we'll take maybe a minute here. Maybe check your code with someone next to you, and then we'll go from there. Or if you don't have anyone next to you, you can talk to yourself. Or phone a friend. You can phone a friend. Or move rows. Don't you just love it when people tell you to move seats in class? Okay, someone help me out here. How would we go about writing the answer to this question? Sabi.
So I did 1 minus stats. Like I used the variable h equals 1 minus stats.home.cdf.
Okay.
And then I used 9 and
Yeah.
the location, the mu, and then scaled a standard deviation.
Okay.
And then I printed the h, and then I got 0.115, so on and so forth.
0.115, nice. So just like this. Yeah, very nice. You also saw that Gemini knew exactly how to write this. Sometimes I'm going to ask you some of these kinds of questions on your homework. I urge you to treat this as practice. Like, make sure that you know how to write these things. But the general guidance for how to use code here, or Gemini, you can add a comment and then paste your question into the line. and it will often give you some answers. In this case, it's not doing it inline, so you can copy the question and put it into Gemini, and that will give you a little bit of help with the code. So here it gave us a little bit of help. So this is actually almost exactly right. And sometimes that can help bail you out of confusing situations. But the general guidance for me, use this only once you feel comfortable with the tool that you're asking Gemini to use. I use AI all the time for help doing things, but I don't ask AI to do things that I don't know how to do. So that's my general guidance. These tools are out there, widely available. In fact, they're built into notebooks, which we're using in this class. But use them with discretion. Yeah, Savi.
So when I was using Gemini, at first I got the SF instead of the CDF. So I tried both ways and I got the same answer. So how is...
Okay. So it was SF?
But without the 1 minus. So it was just stats.form.
Okay.
The whole thing.
Yeah, there are lots of functions within Norm. This would just, I guess, be the survival function. So yeah, 1 minus the CDF. So you can hover over it and it'll give you some extra info about what it's doing. Okay. But yeah, I'm going to use a CDF because that's how I think about the problem. Okay, any other questions here? One last question. How much sleep does the middle 92% of the population get? This is a hard question if I were to ask this of you using like a stats table, but we can answer this question pretty straightforwardly using Python. So the first thing we always do with these kinds of questions is to make a figure. So start by making a figure, and then think about what you would need to find the answer to this question. Okay, I hear very little communication. I'm assuming this is like that you're communicating telepathically. Someone tell me what you were telepathically communicating to the people around you. Yeah, Darren.
I think it would just be the middle two parts, and then on the side would be 4%.
Okay, so nice. So we want two numbers, and on the outside we need this area to be, these areas together to be 8%. We need the middle part to be 92%. So this should be 92%. And then these outside pieces together to add up 2.8, which, as Darren is pointing out, should be 0.04 on either side. Okay, so that's what we're trying to do. This is like the picture of the thing we're trying to find. And we want to find these two numbers. So this is upper bound, and this is lower bound. Nope. Pretend that's correct. Upper and lower. Okay, and it turns out Python has some nice convenient code to be able to do these things. All we want is the fourth percentile. We want to, this is right at the fourth percentile. And this is going to be at the 96th percentile. So this is 0. 0.04. And this is 0.96. So we have 4% that's greater than this, and we have 4% that's less than this. So these are the two percentiles. It turns out Python has a really nice way of doing this. This is the figure. We're trying to find these two values. All we have to do is look up, we just use ppf, which is just the code for finding the percentile. So if I copy this in, I have the 4th percentile and the 96th percentile. You can hover over the function to tell you what it's doing. Percent point function, this is just essentially, you're familiar with like an inverse of a CDF, potentially. We're just basically finding the percentile that's below it. So if I run these two things, I can get the upper and lower bound. Lower bound looks like this. If we put item on the end, it gives us a nice number. So this is the amount of sleep that the bottom 4th percentile gets, which is a terrible amount of sleep. I hope no one gets this little sleep. And then you can find the upper bound as well. So this is much nicer. As a new parent, I am not getting this much sleep. Okay, any questions about this? I'm gonna practice, I'm gonna have you practice much more of this in your homework. There'll be a bunch of questions I'll ask about random variables and probability functions. Treat this as a bit of refresher. You've seen a lot of these things before, maybe not working with probability functions in exactly this way, and almost certainly you'll have not worked with these functions before. But these are just doing the standard statistics things that you're familiar with. Okay, any questions here? So this is nice. This is what we can do if we know the distribution. But in general, we don't know the distribution. And that's almost the whole point of what we're about to do. So I just want to walk you through, I think this is, I keep claiming that this is one of the biggest ideas in science. This is like everything we do that involves observing things, which is how we know anything in any area of science except mathematics. All of that relies on being able to infer something about a population while only observing the sample. And in general, we do not know what the underlying distribution looks like. So if all we see is the sample, how do we learn about the population? Okay, I've asked this question already today. This is what we just walked through. So this is random variables. If we know them, we can calculate anything we like. It's just a matter of doing the math. But this is only true if we know the distribution itself. So I've shown you all these pictures already, but this is the main question. How do we use the sample, which is drawn from the population, to then infer something about the population directly? Okay, so the rest of class, we're going to be spending collecting data. I have a notebook with a computer die, computer dice. And we're just going to be rolling some dice. We're going to pretend for the rest of class that we actually don't know what the distribution, the probability function of dice looks like. We're going to pretend for a second that we don't know what it is. And we're going to start with something incredibly boring. And then we're going to build up one of the biggest ideas I know of. So first, y'all excited for this? I keep hyping this. I was explaining this to someone, like a friend of mine, and they got excited about it too. So I'm hoping, I'm hoping this is fun for everyone. So all I need you to do is hop over to part 2.3, sampling and the central limit theorem. I've constructed a second notebook for you. So I want you to click on this. And what we're going to do is start off very boring and very simple and just roll a bunch of dice. So let me show you how this notebook works. I've written a couple of Python functions here. You don't have to understand how these work, but these are basically just functions that will let you roll some dice on a computer. And we're going to roll like thousands and thousands of dice today. But we're going to start off very simple. You're just going to roll dice once. I looked this up. Dice is both singular and plural, although you can use die for the singular, but dice also can be used as a singular. So I don't like saying die, so I'm going to say dice. Just my personal preference. You can say die if you like. Just don't use dice for singular. Okay, so if you run this cell, you will load these functions that I've written, and we're going to use them to just generate some samples. And pretend for the rest of class that we do not know what this distribution is. This is, to us, an unknown distribution. We know what it is. Like, you know the distribution of dice, right? It's equal weight on 1 through 6. But we're going to pretend that we don't. So if you run this first cell, you're calling this function sample, and you're asking it for one die roll with a sample size of 1. So you're just rolling one die, and it's going to give you a number. Each of you is going to generate one number, and then I'm going to go around the room, and I'm going to ask you for the die that you rolled. I don't have enough dice to give each of you one, but imagine that I've given you each a dice, and I'm asking you to roll it. Then I'm going to enter the data into this notebook. Okay, you all ready for this? You hyped? This is so boring. Okay, so I rolled a 3, so I'm going to enter 3. And then we're just going to snake our way through somehow, and you're going to tell me numbers. I'm going to be looking at my computer, but I want you to just list off numbers for me as we go around the room. And then just make sure you've answered, you've given me a number. Are we ready? 3? 2? Maybe we'll start, should we start in the front and then we'll just weave our way back? 1? 3?
4.
4? 3? 5? 3? 2? 1? 5? 6? 2? 7? Is 7 possible?
Six.
6. Did you get a 7? You got a 7? Did I make a mistake with my function?
No, I think I did.
Okay, yeah, nice. 6?
1.
3?
3.
6? 3? 6?
2. 5. 3. 5. 6. 4.
Okay, so each of you has a sample. You've drawn one observation from our random variable, which is what we're doing when we roll a dice. There's a random variable, and each of you are making a single observation from that random variable. So each of you has a sample. You have a sample size of one observation from the random variable. So your data set as an individual is just a size of 1. So for me, my individual sample is 3. So that the average of my sample is 3. Pick 3, my lord. No one? Shrek? Original Shrek? Anyone? Okay. Okay, tough crowd today. I just fried your brain with a mini exam. So all I'm going to do is take each of your samples, a realization of the random variable. It is both, because it's a sample size of 1, it's both the observation and the sample at the same time. But I'm going to plot all of them. And you're going to identify on this figure where your data lives. So I'm just going to put into a hist plot just all of the data. And it looks like this. Let's specify the bins. We have 1, 2, 3, 4, 5, 6. I think that'll look a little better. Okay, someone tell me what you've noticed here. Yeah,
I guess a lot of 6s, it seems.
a lot of 6s. Yeah. So the mode in this case is 6. Darren?
I think it's 5 bucks.
You're right. Yeah, so, yes, so the bins, yeah, we need 7 bins, or 7 points to create 6 bins. So this should be better, thanks. So maybe we'll revise our estimate. Yeah, so 6 is not the most common. What we were doing was merging 5 and 6. So what's funny about these hist plots is the numbers are, they start at the beginning. So it's like 1 describes what follows. So we have 6 bars now correctly. What do we notice now that we've done this correctly? Our mode is 3. Does this look like equal probabilities for each of the values? Why are we not seeing equal values? Yeah. Yeah, so we don't really have a lot of data for each one of these bins. So it doesn't come out to be nice and smooth like we would expect. The true probability function is just a straight line, equal probabilities for each one of these things. And because this is a sample, we don't exactly see the true distribution. So if I were to look at this and think about what the underlying distribution actually was, I would not be able to infer it from this. Like, I know that when I roll a dice 1,000,000 times, it's going to be basically equal across all 6 of the values. This is a fair dice. And even with this many observations, how many observations is it? 35 observations. Wow, that's really low. Where is everyone? 35 observations, and this doesn't look uniform to me. It doesn't look like we have equal probabilities. So this is the first observation, right? That just because we're drawing from a distribution, even 35 times, we're not going to correctly be able to identify what the distribution is simply by looking at the histogram. So remove from your brain this idea that you can identify what the distribution is simply by looking at the data. The underlying distribution does not match the observation. Sorry, the underlying data, the underlying probability function does not match the data. Or you at least won't be able to infer it from a small sample size. Okay, so this is the first observation. The next thing we're going to do is actually take a larger sample. And instead of collecting data on on one observation, we're going to collect data on the average of 2. So each of you is going to roll 2 dice, and you're going to report to me the average of those two. Thankfully, I've constructed a bit of code here to be able to create a sample and then find its mean. So I'm going to run a sample here. I get 6 and 2, and then I'm going to find the mean of that, which looks like this. And if I run it a bunch of times, I get different numbers. I just need 1. So my observation here, my sample mean with a sample size of 2 is 2.5. So I'm going to say 2.5, and then we're going to go around the room, and I'm going to collect the data again. Everyone clear what we're doing? 2 observations. I'm not looking for both of your observations. I want you to just take the mean, the average of the 2, and then tell me that number. Okay, we ready? 4.5. 2.5. 6. Wow. 2.
4.5.
4.5. 3. Oh, hold on just a second. Savi reported 6 to me, which is possible. What that means is that she got 2 6s. There's only one way for that to happen. Be thinking about that as we report these numbers. There's only one way to get a 6, which is that you get 2 6s, because the average has to be 6. Yeah. 3.5. 3. 2.5. Oh, and sorry to pause one more time. To get a 3, there are actually multiple ways to do this, right? You can get 2 3s, you can get a 2 and a 4, you can get a 1 and a 5. And I think that's it. There are multiple ways to get a 3, but there's only one way to get a 6. So be thinking about that idea. Alexa. 4. 1. 3. 4. 3.5. 3.5. 5.5. 2.5. 3. 5.5. And I think there's only one way to get a 5.5, which is a 6 and a 5, right? So you both got 6 and 5. Yeah, nice. 2.5, 5, 2. And even though there's one way to get a 5.5, there's actually, I think, 2 ways to get a 5? It's either 6 and 4 or 5 and 5. Nice. 4. You're up.
Oh, I'm sorry.
2. Okay. 4.5. 3. 3.5. 4. 5. 1. And 1 is also one of those rare cases where there's only one way to get it. You have to roll 2 1s, which is what you got, right? Yeah. 3.5. 5.5. 4. And 4. All right, so I'm going to enter this as data. We're going to run this as a histogram, and we get something that looks like this. So let's do bins. Let's go range 1 to 7, 0.5. Let's not specify bins. I guess you could go 1 to... Yeah, let's just ignore this for now. Okay, so this is our data. We have... Actually, I think we should specify bins. Let's say 0, 1, 1.5, 1, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, and 6. And then we need 6.5 just to give us the upper bound. All right, so this is what our data looks like. So someone tell me what you're seeing here, and maybe why. Darren.
It looks more like sort of like the graphic they had in the slides before. I think it's
Yeah.
because there's a higher probability of getting the numbers in the middle because there are more combinations to get them.
Right, so what Darren's saying, this figure looks like there's more weight in the middle. Sabi got a 6, which can only happen one way, which is 2 6s. We also got a couple of 1s, which can only happen one way. There's only one way to get very extreme values, where there are many ways to get a middle value. How many of you play Settlers of Catan? Okay, no one watches Shrek. No one plays Settlers. Who are you people? So I played a lot of Settlers of Catan. You roll 2 dice in Settlers, and then depending on the sum of the 2 dice, a bunch of different things happen in the game. 7 is the most common outcome, which turns out to be a very unusual thing that happens in the game. 7 is the most common outcome because it can happen the most number of ways. It can happen with a 1 and a 6, a 2 and a 5, all the way until it's 6 and 1. This can happen many ways. So we see 7 the most often in Settlers. The same thing is happening here. I've asked you for the 2 dice, you take the average of the 2, and that gives us a middle value, which is the most common. So we get this sort of pyramid shape. I have this in the slides, actually. So this is I ran this 1,000 times instead of just the 35 that we had in the class. This is just a sample size of 1. You can see this is exactly or pretty close to what we would expect when we roll a bunch of dice. Basically equal values for each of the 6 numbers. When we roll 2 dice, essentially what we're doing is we're collecting 2 observations and we're finding the average of the 2. So each of you performed this operation on your data. You had 2 observations and you took the middle, the mean of the 2 and reported that number to me. And it turns out there's lots of variability here, right? There's variability within your sample. Each of you had a slightly different number. And when we plot those means, the distribution of the sample mean when we have 2 dice, we get basically a pyramid, which is what Darren is observing. We essentially have a pyramid where the most common value is in the middle, and then it's symmetric and it falls off equally on both sides, just linearly on both sides. And I think what Darren was observing earlier is the reason this is happening is because middle values can happen in many different ways. Okay, this feels intuitive. Slightly boring. Maybe a little bit more interesting than the first one. I think 2 dice is more interesting than 1 die, or 1 dice, as I will insist on. And the basic idea is it's much more likely to happen with a 3.5 is much more likely to happen than a 6. Okay, we're going to do this. I'm not going to collect the data this time. You're going to actually run 1,000 observations on your computer. You're not going to hit the key 1,000 times. You're just going to have Python generate for you 1,000 observations. And then we're going to plot the distribution of the samples. Okay, so I've actually written some nice code for you here. We're going to have a sample size of 3. So you're going to roll 3 dice. You're going to take the average of those 3. You're going to put that in a data set, and you're going to do that 1,000 times. So the picture to have in your head looks like this. We're going to collect 3 observations, and then we're just going to do this 1,000 times. I have a picture of 5 of them, but you're going to do this for 1,000 times, and you're going to record each of these X bars, each of the sample means. I've written you a little function called samples, where you can enter the sample size, which in this case is 3, and then you can enter the number of samples, which is 1,000. And that's going to return to you the sample means for a sample size of 3, which is an entire data set in itself, which you're going to generate. So run that. And let me just show you what this looks like. But we're actually going to make a histogram of this thing. This is a very large data set. It has a bunch of numbers. This looks a little scary, but we have 1,000 observations in our data set. Just a huge, long list. But this is one of those cases where data sets are best understood with a summary. And a histogram, you could use a box plot here too, but I think a histogram is the best approach. So I'm going to create a histogram. I've given you the number of bins, so you can just run this. Maybe 15 is better. How many of you get something that looks like this? How many of you did not get this? Slightly wider?
Well, 2 peaks.
2 peaks. Oh yeah, maybe like a peak in the middle, but it's maybe spread out a little bit, and the middle bit is kind of dipped. Yeah, but it generally looks something along these lines. You could increase the sample size. In fact, it'd be very easy to take 100,000 observations and run that. It'll take a second, but you could plot that, and that would look very, maybe more consistent. If you try that, I think that would fix your problem, or fix your exact sample. You could also run this a bunch of times, and each time you run it, you're going to get a different distribution, because you're just collecting new data every time. Each time I run it, it looks slightly different. Okay, so what does this look like? What do you notice with the shape here when we have a sample size of 3 and we run this a bunch of times? How is this different than the first 2? We're starting to like enter the world of maybe it's interesting. Yeah, Kurt.
Starting to get a little smoother, like similar to the, whatever that's called.
Interesting. So we have a distribution that looks normal over here. You can hold this in your head if you like. What Kurt, right, is saying is it's starting to like have some curves to the line. It's no longer just a pyramid, and it's definitely not flat. There's some curvature to it. Yeah, Jason.
I was also just going to say it's starting to look more like a normal distribution.
So it's starting to look a little bit maybe like a normal distribution. So if you're familiar with a normal distribution, maybe your spidey sense is going off a little bit here. That's what I see too. So I'm going to overlay a normal distribution on top of this massive sample size that I ran. Why do you think this is happening? Like truly, what's the thing that's happening here? Tell someone what you think. Like, what's your hypothesis for why this is happening? Why are we getting some curvature to it? What's going on with this distribution? We went from 1 to 2 to 3. 1 was very boring. 2 was maybe a little more interesting. We get this third one. What's happening here? Just say something intelligent, intelligible to the people around you. It doesn't have to be intelligent.
Because as we have a greater sample size, yeah. Yeah. But the more you take, the more it's there's due to the list is the central.
Okay, so someone want to tell me what's happening here? Why are we getting this kind of squishing towards the middle. You can say central limit theorem, but that doesn't actually get at the idea. What's happening is middle values are just much more likely to happen. Just like when you roll 2 dice, 7 is the most likely. When you roll 3 dice, it's even harder to get extreme values. To get an average of 1, when we have 3 dice, all 3 of them have to come up 1, which is much harder to happen than when it's 2. It's like 1/6, where the middle values, as we start increasing the sample size, have much more of a pull to them. They're much more likely to happen because the extreme values become very unlikely. Okay. So in your notebook, you can see I have another bit of code to run sample sizes of 30. So you're rolling 30 dice each time, and you're going to roll 30 dice. You have like a huge handful of dice. You're going to do that 1,000 times. And we're going to look at the distribution of 1,000 30 die rolls. So I'm going to run that. It ran instantly. That's what computers can do for us these days. And then you can plot a histogram of those things. Okay. Turn to your neighbor, describe what this distribution looks like, and maybe in one sentence, try to convey some of the intuition for why it looks this way. What do you see? What's a general reason for why? And you can't say central limit theorem.
Because we increase the same size as opposed to the number of samples. So because of that, do the sample size and do a little more. Whether it's a 1, 2, 3, 4, 5, or 6, the more we do that, the more outcomes we'll be able to have that are more gravitate more towards the mean of 3, 5. So you're not less than this relative to how many you have to total. So that's why it's becoming more complex.
Okay. Someone tell me what you're seeing and tell me why this is happening. Yeah. Yeah. So the distribution is very narrow because it's very hard for us to get extreme values. To get an extreme value, we have to get 31s. Do you know what the probability of 31s is? It's what? 1/6 to the power 30, which is basically 0. You basically cannot get a 1 in this case, where getting values in the middle becomes very common because the extreme values become uncommon. That's the intuition here. We get this bunching in the middle because extreme values basically do not happen. So we can do this one more time. We're not going to spend a lot of time talking this through, but if you want a sample size of 1,000, you can plot this. And again, it has this shape to it. I've done this in the slides. I think this is very unboring. We started with a sample size of 1, we went to 2, we went to 3, then 30, now 1,000. And it looks like, I mean, each time we do it, it looks increasingly narrow. So this is on the same scale. The distribution, each time we increase the sample size, gets tighter. And it becomes maybe a little bit more like a normal distribution. Each time it gets tighter. As we go to 1,000 observations, it gets so tight, there's very little area that's not outside of like 3 to 4. Everything's really between 3 and 4. So this is the basic intuition for what's happening here. As we increase the sample size, it becomes very unlikely for us to get extreme events, which centers the distribution of our samples. Each time we draw a sample, it becomes harder and harder as the sample size gets larger. It becomes harder and harder for us to be far from the truth. You all know what the truth is. It's right here in the middle. It's at 3.5. The average die roll is 3.5. And it turns out as we increase the sample size, we get close, the probability of being far away from the truth, from the average, goes down. And a couple of you have pointed out what this red distribution looks like. This is the normal distribution. We're not going to do the derivation here. If you're interested in the math behind why this is true, you can take classes on this. But the basic idea for what we've done in this class, we started off with known distributions. These are things we can deal with. But we had questions about what we know when we don't know the distribution. Can we do anything when we don't know the distribution? And the answer is you remember when we just drew 35 observations from a die, it did not look like a uniform distribution. We can't simply look at the distribution and easily infer what the underlying population is. Our sample did not match the population very well. But what we do know is that when we take repeated samples from an unknown distribution, every time we increase the sample size, the distribution gets closer and closer to a normal distribution that's centered on the truth. And the probability of being far from the truth becomes smaller and smaller as the sample size gets larger. It becomes much harder for us to get extreme values when the sample size is very large. And this is the central limit theorem result, which is that the sample mean itself follows a normal distribution that's centered on the truth. Or I should say it more precisely. As the sample size gets larger, the sample mean gets closer and closer to a normal distribution centered on the true mean. So X bar is centered on mu. Mu is the population mean. And it turns out we don't need to know what the underlying distribution is to know that this is true. As the sample size gets larger, this gets tighter and tighter, so it becomes harder for us to be far from the truth. I don't know, I put an emoji. This is the only time there'll be an emoji in the slides. This blows my mind that this is true. I mean, in some ways, as we walk through this progression, it hopefully feels intuitive to you that this is true. But the fact that this is true is what allows us, I mean, there are two parts, right? There's the centered on the truth part, and then there's the normal distribution part. Because both of these things are true, this allows us to know what the distribution of our sample mean is, without having to know what the distribution of the population is. And once we know what the distribution of the sample mean is, we can then do these kinds of things on the distribution of the sample mean. So we can do this stuff even though we don't know the underlying distribution. Okay. My mind, I talk this thing through every semester, and it still blows my mind that this is true. Okay, so we just walked through a uniform distribution, but not every distribution looks so nice. This is a weird one, and even still, we get this progression. As the sample size gets larger, even though it's not symmetric, we still get this clustering around the truth in a way that approaches a normal distribution. So no matter what the underlying distribution is, we get this result. This is something we can work with. Even though we will never see the underlying distribution, we can work with a known distribution because we know what the distribution of the sample mean approaches as the sample size gets larger. Okay, no homework this weekend. I'll see you all on Tuesday. Go get some sunlight.